All right, so for lecture 3, we're talking about fields, generating fields by objects. So we're going to have a sphere here. We have a big metallic sphere. Actually, metallic doesn't matter, but it's always fun to put extra stuff in there. And that's going to be 25 microcoulombs, right? It's got a 5 centimeter radius, so this is 5 centimeters. And then we want a distance between this guy and this other guy of 10 centimeters. Now this is 10 centimeters from the center of the sphere. And that's when we're using what we're going to use later on, what we use. Okay. So that's what we have, and what we want to do is we want to find eventually the force on this little guy, which is actually going to be equivalent to the force on the big guy. And so we want to find this blue force here. The way we're going to do that is by using the definition of force that we used in the last lecture, F equals QE. So whatever the charge of this is, 10 microcoulombs right there. It's 5 centimeters from the edge of the sphere, so 5 centimeters plus 5 centimeters is equal to 10 centimeters. So this E is going to come from part A, because it's going to be 5 plus 5 equals 10 away from the center, and our field is going to be measured 10 centimeters from the center in this part. So strangely enough, part A gives you part B. It's almost like it was planned. So let's go ahead and do this, right? So how did we say in the lecture part, in the description, we got the field from a metallic sphere, or from a charged sphere? Well, we said it was, use this formula, 1 over 4 pi epsilon naught times the charge. So the more charge you have on this sphere, the more you get. And then the farther away, we got 1 over r squared here, the farther away, the less field you get. So larger charge, more field, more distance, less field. So charge and field are not the same thing. Remember that. I know somebody who was really quite good at all this stuff, but he had a problem differentiating between electric charge and electric field. And so if he was good at this stuff and he had that problem, you might too. All right, so we want to find this field here, E, through this guy. Now 1 over 4 pi epsilon naught, is about equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. Epsilon naught, remember, is the permittivity of free space. That's a number in SI units that basically relates the strength of magnetism. Well, it's the strength of magnetism in free space. So it's going to, or not magnetism, electricity. So it's actually going to be very important if you go on to do more complicated things. It'll deal with what's the field in the material and the field out of the material, and this epsilon naught is going to form a really big part of that. As at this point, it's really just going to tell us that this is the constant that transforms from charge and distance to electric field, the number there. So just said 1 over 4 times 4 pi epsilon naught is 9 times 10 to the 9th newtons meters squared per coulomb squared. The Q we said was this guy, 25 microcoulombs, 10 to the minus 6 coulombs. And then 10 centimeters is 0.1 meters. We square that. Okay, so we have here 9 times 25 times 10 to the 9th here, 9, minus 6 here, and plus 1, 2. So 0.1 is 10 to the minus 1, and we square that, so that's 10 to the minus 2. But it's 1 over 10 to the minus 2, that's 10 squared. So it's 100, but we can just put that in there as a 2. Just shove it in the exponent and see who salutes. Let's see. Then we have units. meters squared and meters squared, so we can get rid of the meters squared, get rid of one of those coulombs, so that gives us newtons per coulomb, which is one way to write the electric field units. The other is volts per meter. So newtons per coulomb is equal to a volt per meter. They're the same unit. We'll use volt per meter sometimes after we get into, things that use potentials. Okay, so where are we? Okay, so we've got 9 times 25. So let's see. 25 times 2 is 50. 50 times 2 is 100. 100 times 2 is 200. So that's 2 times 2 times 2, that's 8. So we have another one, so we have 225. All right, times 9 minus 6, which is 3, plus 2, which is 5. So 10 to the 5th newtons per coulomb. And I guess I'll leave it there because I don't like mega newtons. That's a funny sounding thing. So we have 225 times 10 to the 5th newtons per coulomb for our field. And that's what we're going to use to find the force, right? And remember, force is equal to charge times field. And of course, now we have our charge here, which is 10 microcoulombs, 10 times 10 to the minus 6 coulombs times 225 times 10 to the 5th newtons per coulomb. Actually, this number is 10 to the minus 5, so this number cancels out that number. So we end up with 225 newtons, and we cancel out the coulombs, 225 newtons there. So let's see, did I do that right? I did that right, 225, we're doing good. All right, so that was basically how to calculate the force between two objects, the electric force between two objects. One is you calculate the field. In this case we had a sphere, so we used this. But I also gave you formulas for lines, for cylinders, and for plates. So you have to use the right formula for one of these different charge distributions, one of these different looking charged objects in one of these problems. And then I take that field and I use our definition of the electric field, which is the force is equal to charge times the electric field, right? And then we're done. We got that 225 newtons, and we know how much force is on this guy. We figure out how fast he's going to recede away because they're both positively charged, right? Positive and positive means the direction of the force is away from the other object. Okay, so that's the first of 3 problems for this lecture. Let's see what the second one is.